The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Their presentation is about the use of heavy equipment on existing bridges during construction, and we have Kyle Eyre from Kiewit Engineering.
Thank you, Oscar. Appreciate that opportunity to speak to you here today. I'll be discussing use of heavy equipment on bridges during construction. This actually ties in quite well with the session this morning, if you were here, where we were talking about demolition in Las Vegas, the history there with Joe Eyre and Sigma Engineering. Quite a lot of parallels there between the two. So today the agenda I'm going to cover here is talk a little bit about Kiewit, our culture, our history, where that comes from, and that kind of sets some of the context of why we're doing what we're doing. Then I'll focus in on risk mitigation, what kind of efforts go into place and making sure you keep everybody safe. Talk a little bit about design criteria and what we've chosen to push forward with when we're looking at heavy equipment on bridges, superstructure during demolition or during construction. Focus a little bit on the loading, what you can expect to be controlling. Then I'll mention some of the methods that we choose for the best practices for specifically demolition. I'll touch a little bit on erection as well. And then finally, just some more design best practices, what we would recommend pushing forward with. So a little bit about Kiewit. We were founded in 1884, 4 brothers. Today we've got around 30,000 employees. That includes all of our full-time staff and craft. Full-time staff, we're at about 11,500 or so. We have about 1,300 engineers across the company, which is something that not a lot of people know. We actually have efforts in place to grow to 2,000 engineers here within 2 years. So it's just kind of a staggering thing to think about. We want to have the right kind of growth. And what sets us apart here is we do have the core values of people, integrity, excellence, and stewardship. And that's something that drove me to the company here, almost 10 years ago, and I'm going on 35 years. It's the kind of place where you can spend a career. And I'm a structural engineer, so I've got a dream job because I work for a contractor. And we do a lot of challenging designs and design reviews, and really we see some of the highest loading on the bridge superstructure during construction, during demolition, that it would see in the service life. So then along with that, and kind of tying in well with Joe Eyre's session here this morning on risk, that's something we take quite seriously, in that we do have a corporate policy at Kiewit that there is risk. We understand that we have risk. We build this work. We know that at times we can see the highest risk during construction, during construction of an operation. And to respond to that, we created a policy that basically says, okay, we have risk. We need to mitigate this risk. We need to take the proper action and measures to reduce that risk. So one of the responses to that is that here's that corporate policy here, but we've developed a manual that helps us to address and mitigate the risk. Just a little bit of background to some of the, say, consulting, structural engineers. We do have temporary structures and construction devices. Many of these are created in order to aid the construction to get to that final condition where it's a final structure. But in that process, there are all these permanent works. There are all these temporary works that go in support of the permanent works. So many different types of structures that you can imagine: formwork, false work, supportive excavation, cofferdams, staged construction, staged deconstruction. This is all something we identified that we need to cover. We need to help mitigate risk. The basic philosophy is that we'll conceptualize, design review, inspect, and verify. So this document here is something that I've seen put together around 20 years ago. It's really been well defined and implemented throughout the company. It's a requirement for every project that they follow this. It's actually revised sometimes annually, sometimes twice a year. Really well done. It spells out that philosophy of identifying the temporary structures, the temporary works on the project, analyzing and categorizing the risk. So ask yourself 2 basic questions. Okay, during this bridge demolition, what's the worst that can happen? And then on the same side, you ask, okay, what is the likelihood of that? And so you can kind of play off of those to see the different impacts of, say, safety, worker safety, exposure to public, your reputation, impact to cost and schedule. Based on that, we can categorize the risk of certain operations, certain temporary structures, and then as a response to that, we mitigate the risk by selecting the appropriate designers. We wouldn't have an intern, 6-month intern designing a high-risk tower crane foundation that's in downtown Seattle. So we take the right measures there. We reach out and we do collaborate. We reach out to the subcontractors and consultants that specialize in some of the work we do. And then we document and verify, so we have a very robust inspection and re-inspection program to make sure that the structure is being built accordingly. So for a good example on heavy equipment on bridge superstructures, we have a table in our manual, permanent structures, temporary condition during construction, and erection. And you can see there are different categories in here, low, moderate, or high risk. And in response to those, then we implement different requirements, different levels of requirements for who is qualified to be the designer, the design review, the independent design review if necessary, and then the inspection. So along with this, we'll ask ourselves those two questions: what's the worst that can happen? And then what is the likelihood? That helps us to categorize the risk that we agree upon with the project team building the work in order to identify who are the right players. So now shifting gears a little bit and talking about design criteria. So when we look at loading heavy equipment on bridge superstructures, as Joe mentioned earlier this morning, there's really not a lot of guidance out there. You can go to OSHA, you can go to IBC. There's limited guidance. What we found is that our go-tos are the ASCE 3714, design loads on structures during construction. There's very good guidance in there, and we'll follow ACI 318. We'll look at AASHTO, the LRFD bridge construction spec, the load factors in there. There's also the guide design specification for bridge temporary works in AASHTO. And then we'll also reach out to other resources if needed, say AREMA if we're dealing with rail, or I just co-authored an internal construction engineering design criteria. So similar to that manual that we've got for temporary structures and construction devices, more readily used on project sites to categorize the risk and then mitigate that risk. Now in-house with that Kiewit engineering group, we've got this document here to get us a good starting point in order to have a good path forward with putting together the numbers for some of these structures. Talking a little bit about dead loads here. So a lot of these operations, will have a controlled environment, very limited time, and we'll need to make sure everything goes according to plan. So one of the things we'll look at is taking into account all the different dead loads that we can identify. A lot of pre-inspection, a lot of conversation and site visits with the project to identify everything that's there. Self-weight measurements, if we don't have good past drawings to go off of, a wearing surface, barriers, any utilities that are there that need to remain in place, say adjacent to the new structure sometimes. We do recommend AASHTO 3421. There's a design load for 1.25. It's looking at the max force effect during construction. We'll actually be conservative and we'll go 1.5 if we have dead load only cases where the excavator is not on the superstructure. Moving on to live loads. Many times it's equipment self-weight that we need to capture, the dynamic impact effect of obviously these hydraulic hammers that impart vibrations to the structure. So AASHTO 3421 as well, live load of 1.5, impact factor of 1.33. We'll follow this fairly strict guidance here because we do want to know that true safety factor. We don't want to be pushing the limit and having a structure that becomes unstable, because what we're doing is electively reducing that stability of the structure in a very precise manner so that we know how much we can take away before we are at risk of collapse. But we want to take away enough that we can move that material to the proper equipment to basically safely take the thing down. So a little bit more with equipment here. Many times the excavator on the superstructure will govern. It'll be the governing load case. The typical excavator is going to weigh anywhere from 30 kips to almost 250 kips. It really can go that high, and as a contractor, I'll tell you, we will try to put the heaviest excavator on that superstructure that we possibly can. The reason being is that it's going to have more power. It will be able to take out more material more quickly, and so in our mind, if we can adjust designed for that weight and understand what our true factor of safety is, then we can minimize the operation time and cycle for taking that bridge down. If we were to use a lot of equipment that's 5,000 pounds or less, sure, we could do it with minimal impact to the structure, but then it would take forever. You'd have a lot more exposure to the workers, to their safety, to public and their safety, especially if they're underneath one of these bridges. And many times, the economics just don't work out where we do have a weekend closure, so we can't have the luxury of time there. A lot of the operations are well planned if you can eliminate heavy equipment on the superstructure and utilize ground-based excavators with large booms, and you can reach up high, as well as a ground-based crane to lift out sections of the deck itself. A little bit more on equipment. I mentioned here the 40 to 100 kip range. That's our optimal range, what we've seen that most superstructures, typical construction can take. We do have, the option of heavier excavators, but then there are more challenges design-wise. So the optimal range we found is between a 40 and 100 kip excavator. And we compare that back to, say, remember the Ashtoe design truck at 72 kips with the two axles in the back and the one in front. So you can kind of see that we're putting higher loads on the superstructure than it was intended for. And so what we do is we look at, okay, what's going to be our worst loading case? Many times it actually is the crowding effect, or it's called the dynamic position for the excavator, where the boom is pushing down with its nose, pushing down with that hydraulic hammer, and then it's kind of going back on its heels if its tracks are forward. So you think about all that nice uniform distributed load on the tracks, you push down a little too much and you go back on your heels. That can kind of spike to concentrated loads that are higher than the deck the allowable capacity of the deck would be. That also, if your tracks are turned 90 degrees and you're leaning over the side too, you can have a shorter distance between those concentrated load points. So that's something that we will always look at, rather than just a specific total dead load and a uniform distribution across the whole tracks. There's many different methods for deck removal. Some of it is, you do some initial core holes to start and do a deck slotting operation. This obviously reduces the girder's stability, so we don't want to take away too much. We want to take away just enough. And one of the things we do recommend is to have the diaphragms remain in place as long as possible until the very end, when you do go to take down that final girder, that single girder. Diamond blade saws, those are expensive. They're generally recommended for a limited application of cut lengths. What we do prefer and what we've seen in the past is a diamond wire saw is the most efficient. You can cut large swaths in a short amount of time. You can get a clean cut. There's a minimized, reduced amount of vibration to the structure that occurs. So that's something we will kind of start with as an option of, let's do a slotting operation and then move on to a more mass removal, and I'll kind of show some examples of that here. And then once you're finished with the operation, you can see everything is pretty mangled, and we'll look at crane capacity and ground-based cranes and radius to make sure we can lift the segments that are in there. So it's not a simple linear it's not a simple approximation of the total weight. You've got to account for the pieces that are mangled in there. Obviously, a lot of this work is occurring at nighttime. There's limited visibility, and part of that superstructure is all still attached with all the reinforcing. So you get torches and you get flames that cut through the rebar. Here, this picture on the right shows the deck slotting operation and what is still remaining after the cuts occur. So the finished product would be similar to the erection operations, where you have a single girder that's set, and we do look at the stability of that girder. We look at resources like mast to understand what the capacity is and make sure we don't take away too much. A big part of that planning and the risk mitigation is the staged sequencing. So we want to make sure to evaluate every step along the way and understand that you've got a reduced wind capacity, reduced wind exposure. There's an example here that kind of shows a typical phased demolition demolition process. Typical cross-section here, you've got a bike path on the left-hand side, and then your lanes of traffic on the right. This kind of schematic planning effort goes in hand well before the operation, so that everybody, all the team members are understanding what is involved and what we're going to be looking at. Here, step one, we'll remove that outer barrier rail, saw cut in 10-foot pieces, pick with the excavator and set it onto a haul truck. Sometimes these haul trucks can be 150 kips. So you're thinking a 70 plus kip AASHTO truck versus 150 haul truck. So sometimes we'll have to get creative in reducing the loading to the deck to make sure we don't have cracking issues if it's going to remain in place after, if this is a widening operation. If it's going to be remaining in place, we'll look at staying under the cracking stresses. Stage two, removing the outer bike lane deck, saw cutting into 10-foot pieces, picking with the excavator. This is a fairly efficient operation. And then next step, removing the inner barrier rail, the HOREM excavator for demolition. So this is all occurring, work overhead. This view, this isometric, shows a little bit better of what ends up remaining. So removing the inner bike lane deck, saw cutting into 10-foot pieces, picking with the slab with the grab and loading directly into the truck. We'll look at that loaded truck, and sometimes that could govern our deck analysis, our deck capacity. And we can throw a crane mat on the deck to spread loads out. We can come up with a mini grillage if we need to reduce loads and bypass the deck. But that is definitely like a last resort there because of the time that it takes to set that up with these limited closure windows. Stage 5, using the excavator with the shear to remove the existing girders and stringers. Girders are picked with full length with the crane from the trestle. This was an operation where it was over some water here. Final step, or stage 6 here, wire saw the existing bend and top of concrete piles, picked with the crane from the trestle. Stage 7, shear the existing piles, 16-inch concrete with the excavator sitting on the existing bridge. So all of this to go that, it makes sense to plan this well ahead and make sure all of the steps and stages are accounted for so that we can zero in, we can understand what is going to be governing for us. You can see there's a lot of dust. I know that was one of the questions that popped up earlier this morning was, what kind of measures can you take to control that? Many times we'll have a blanket down of soil underneath the superstructure to soften the area underneath so that the falling debris doesn't impact the road pavement. And then we'll have water spraying as well so that finished products end up looking like this to be able to take down. This was obviously not over an existing roadway. That is a more challenging effort because all of that material has to be cleared out by a certain time Monday morning, or you get hourly liquidated damages that are in the hundreds of thousands of dollars. So some of the design best practices, obviously come in and add supplemental support when necessary. One of the stages in here that we ended up doing is to reshore and resupport that bent. You can see this false work underneath. Based on the stage deconstruction here, we wanted to place the support where it needed to be. On the photo on the left here, we've got a utility that needed to be supported remaining in place. So we've had a temporary false work system for that. When evaluating each stage, you want to do it efficiently, obviously starting with hand calculations. Don't jump right into a black box. That's something we've always kind of shied away from, is we want to understand first what are we really dealing with, then jump into something like RISA 3D or Midas Civil. Midas Civil has the capabilities of supporting the staged construction or deconstruction sequences, locking in those time-dependent stresses. It's pretty valuable. But for a lot of the run-of-the-mill, say a TxDOT bridge superstructure demolition, we can utilize RISA 3D very efficiently, understand, what is our capacity, what is our demand, and just kind of push through that. Obviously, consider your risks. You've got high-risk safety. You've got workers exposed up there on the superstructure. You've got high-risk cost if something goes wrong, if a structure comes down adjacent to a new structure and causes damage to it. If your road doesn't open up, the time window, there's huge liquidated damages that can occur. Adjacent structures, and considering that. We do like to, as Joe mentioned here, plan the work and work the plan. We'll definitely reach out to consultants that are specialized in that, like Joe there with Sigma. More design tips, use conservative load factors. We don't recommend any deviation from, say, the highest limits that we've seen. There's particular language in the ASE 3714 that allows a temporary reduction to the load factor based on an arbitrary point in time. That's, knowing how long your operation is and the known loads of your equipment. We never really deviate from that and go too low. Serviceability is huge, especially if you've got a superstructure where it's newly constructed and we are looking to put heavy equipment on it to move materials. We want to make sure that we look at the serviceability limit states and understand that we're not going to put stresses on the structure that cause cracking. That's a big one, and what we found to mitigate that is to use smaller equipment, more cycles, or use crane mats to bypass the deck with a mini grillage. And then typical excavators keep those at around 80 kips, not too high, depending on what the capacity is, though. Final design tips here: just crane mats if necessary to protect the deck. That is the weak spot of the superstructure. Usually, you can minimize that impact with some crane mats to soften, spread out that load. Low distribution frames if necessary. Sometimes we've put crawler cranes on bridge superstructures, and those obviously are heavy track pressures, and we'll utilize a heavy grillage frame to bypass the deck to go right to the girders if the girders have the capacity. And then providing temporary false work, shoring if necessary. Obviously, having a plan and making sure you've got qualified people working on it and reaching out. We do reach out to a number of consultants there that also share in our efforts. All right, so with that, I'll open it up for a couple of questions here. Thank you.